Hello and welcome to Empowered Learning. This video will be a continuation of the video on calculating volumes of a solid by slicing, disk, or washing methods. We're now at the point where we're going to start doing some of the examples. And so these will be examples of situations where we have non-solids of revolution, meaning that we're taking an area, taking a solid that is formed by stacking a bunch of areas basically on top of each other. Okay, so for this problem, we have a solid that is being formed by basically taking planes perpendicular to the x-axis of x equals 0 and x equals 15, and the cross sections perpendicular to the axis are squares, where the diagonal that runs from that parabola runs from the parabola here and here, okay, or the -2 square root of x to the parabola y equals +2 times square root of x. So the first thing that we need to do is sort of get a picture of what this is going to look like, okay? Now, if you remember your square root functions in general look like this, okay? And so we know that 2 times square root of x is a variation of a theme on that. Of course, negative 2 times square root of x is going to look something of this type here. And of course, if we put both this and this together on the same graph, then of course what we have is something that looks like a parabola where it is a function defined in terms of y, okay? So we need to, first of all, draw a picture that illustrates this, but at the same time, it also lets us know within what x values we have to sort of keep ourselves within, okay? So if we're looking at this, let's just draw this. And of course, we're looking at a parabola that kind of looks like this and like that, and we'll keep going from x equals 0 to x equals 15, okay? Now, the other part for this is that we understand that we're basically forming this solid by taking a bunch of squares where the diagonals run from the parabola up top to on bottom here, okay? So to make my point, I'm just going to draw me 2 points here. And so let me try that again. So we'll draw this point. We'll draw this one. So what I'm going to do is to keep it here. We're just going to move that point there, move that point there. And what we're saying is that the diagonal of this particular function of the squares that we're talking about, so let's say this is a square where all the sides are the same length here. Then of course the diagonals of it, meaning from over here to over here, is going to be inscribed by this particular parabola. So if we turn this on its side, it will look something like this, where all the sides are the same. And of course, where the points are, we have a point here, and we have a point there. So if we were going to sort of draw that, what I'll do is, of course, take what I see here and try to draw it here. And I'm going to do the best I can to make that happen. So we'll have a shape that kind of looks like this. And of course, we'll just say this is our area here. So we got a bunch of these little squares where the sides are all the same, okay? And so another thing I want everyone to notice here is that when we're looking at this, notice that the length of this diagonal here is going to be 2 times y. And part of the reason for that is the following. So we know that for this parabola, which is positive 2 times square root of x, of course, the distance from this point should just be y. And of course, down here, this is y equals negative 2 times square root of x. Distance here is going to be negative y. And so the difference in between y and negative y is, of course, 2y. So we have our area, which is this diagonal. And of course, we know that this particular area here is 2y. Okay. So understanding that, what I'm going to do is just turn this around here to try to make this a bit easier to work with. So I understand that the length from here to here is 2y, then it means, of course, coming from this point to this point is also 2y. So halfway in between here is y, and the other half of that is y. And so by knowing that, we know that the area of this upper triangle here, and what I'm talking about is all of this part here, all of this. It's just going to be 1/2 times base times height, where the base is 2y and the height is just going to be y, which is another way of just saying we can characterize it by y squared. Okay, so now that we know this is y squared, we know what y is, right? Y is essentially just going to be this. So therefore, our A is just going to be, our area is just going to be 2 times square root of x, quantity squared. And of course, 2 squared is 4. And here we have square root of x squared, which is x. Okay. Oops. Get rid of that. Now, this is just for 1/2 of the square. So really, for the entire area, this is just 1/2 of the total square that we have. So for the entire area, it's just going to be 2 times 4x, which is 8x. And so if we want to know the area at any one time for this particular square that's being modeled this way, it will be modeled by 8x. So wherever we're at from x equals 0 to x equals 15, we have to multiply that times 8, and that's what the area of this corresponding square would be. So now that we have that, we have what we need to be able to calculate the volume of the solid that's made by stacking a bunch of these squares that are where the parabola goes through diagonally from x equals 0 to x equals 15. So from here we know that the volume is going to be infinite sum of a to b of the area times dx. And of course, our limits, our integration here were told to us. We start at x equals 0, end at 15. The area is just 8x dx. And then it's just a matter of integrating this. So here we know that we can ignore the constant. The integral of, or the antiderivative of x squared is just, of x is just x squared divided by 2. And we can evaluate that from 0 to 15. If I factor out the 1/2 out of the grouping symbols, then 8 divided by 2 is 4. We just have x squared from 0 to 15. And then, of course, we use the net change theorem to evaluate. So 4 times 15 squared minus 0 squared. Of course, that would be 0. 15 squared is 225. And we end up with 900. And that will be 900 square units since we're talking about volume. So this is how we do this particular example here. So as you see, the sort of tough thing to do is to model what the area is, okay? And so once you find out how to model the area in terms of X, or let's say if we ever have a situation where we model it in terms of Y, it gets relatively easy to do the rest of that, because the rest of it is basically doing integration like from Cal 1. All right, let's move on to the next example. All right, so for the next example, same directions, but this time, instead of us stacking squares, what we're doing is stacking equilateral triangles. And so to kind of imagine what's going on here, sort of drawing a picture here to let you know what the base of this shape is, which is basically a circle. And what we're doing is, where you see this particular line here, imagine that you have an equilateral triangle standing up like what you have here. So I've tried to draw this on the side. So we have a bunch of these particular equilateral triangles that we're stacking here from x equals 1 to x equals -1. We're stacking a bunch of them up. And so, of course, the corresponding shape for that will kind of have like a cone shape to it. So it's going to look something, like this. But in looking at it like that, it's a bunch of equilateral triangles that's being stacked on each other. So that's basically what the shape that we're trying to form here. Now, what we're called to do is, now that we know what the particular area is going to be that we need to stack, we're basically going to characterize that, find out what the area is for each equilateral triangle slice, and then just add up a bunch of them from -1 to 1 is on the x-axis. So I'm going to erase this and then get started with the problem. All right, so the first thing that we need to make sure that we recognize here is that, of course, if we're going to find the volume of the solid and use this formula here, our area will have to be in terms of x, and it will also have to be a continuous function. If you notice here, we're given the equation of the unit circle, but a circle isn't a function. So we're going to have to be sort of judicious on how we choose this. Now, although a circle itself is not a function, we know that here, if we go from here to here and use the positive half of the circle, that is a function. We also know on the negative half of the circle is a function. And so all we really need to do here is utilize the fact that this top portion here is a function, and then from that figure out what else we're going to do, okay? So the first thing we want to realize here is that if we solve this equation here for y, then what we're going to end up with is just y is equal to plus or minus 1 minus x squared, okay? All under the square root sign. And since we're just going to use the positive portion for this, we are going to get rid of the plus or minus and just use that. And so we can characterize top half of this circle as the function that we're going to use. And we know that that particular function has a height of y from the x-axis on up to its graph. Now, of course, we know since circles are symmetric, we also know that the distance from here to here, from the negative end of the circle to the x-axis, is also a distance of y as well. And so that's why we have our equilateral triangle characterized this way. And so the distance y plus the other distance y here will end up being 2y. And since the triangles are equilateral, that means that all their sides are the same. Okay, so because of that, we know that not only is this side 2y and this side 2y, we also know that this side is 2y. Okay, but all we really need to know is what this side is and this side is to be able to figure out the height. And so as you can see, what I did is I did a perpendicular bisector from this particular vertex of the triangle. And I know that if I do that, that's 30 degrees, which makes this 60. And now I have a 30, 60, 90 degree triangle. And of course, what we know from geometry, if you have a right triangle where one side is, let's say, y, and another side here is going to, let's say the hypotenuse is 2y, then this side here is y times square root of 3, okay? So using that, we know that the height has to be square root of 3 times y, and now when we characterize the area here, the area is just going to be 1/2 times the base times the height, where the base is going to be 2y, and the height is going to be square root of 3y. And so multiplying that all together, we know that this 2 and this 2 will reduce to 1. And so what we have left is just square root of 3 times y squared. Okay? And thus, we already know what y is. So y is this, the square root of 1 minus x squared. So we just have square root of 3 1 minus x squared, square root of that, all squared. That doesn't look too good, so I'm going to rewrite it. So square root of 3, and then we have square root of 1 minus x squared, quantity squared. And of course, this just ends up being square root of 3 times 1 minus x squared. And so that is how we'll end up characterizing our area in terms of x. And so now from here, all we do is just use our formula, and we know that we can use it from x equals -1 to x equals 1 for this particular area here. Okay. So we'll say therefore the volume is from -1 to 1 of square root of 3 times 1 minus x squared dx. And one of the things that we notice here is that 1 minus x squared is itself an even function. So because of that, we can use our integration properties here and say that this is the same as 2 times from 0 to 1 square root of 3 1 minus x squared dx. And so then from there, of course, we can factor out the square root of 3, integrate the 1 and the x squared by taking the antiderivative of both of those terms, and then using the net change theorem to close it out. So to finish this up, what we'll do here is just write 2 times square root of 3 and integrate from 0 to 1 of 1 minus x squared dx. And of course, if we take the antiderivative of 1, it's just x. Antiderivative of x squared is x squared divided by 3. And we evaluate that from 0 to 1. So from there, we plug in 1 minus 1 cubed over 3. And then, of course, for the second, when we plug in 0, everything will be 0 for that. And then from there, we'll close out 2 times square root of 3. This is just 1/3. So 1 minus 1/3 would give me 2/3. Of course, this is just 4 times square root of 3 over 3. And again, this is volume, so we're talking about cubic units. And so that's how we do this example. And so with this closes out our examples on being able to calculate volumes of a solid by using what's called the slicing method, or as I like to call it, the stacking method. And essentially, what we're doing is dealing with a solid of non-revolution, meaning that we're not rotating an area about an axis to be able to calculate the volume of that particular solid. Okay? So if you check out the next video that I'm going to make, it will be about calculating the volume of a solid where we do have solids of revolution, meaning that we have an area that's defined and we're rotating that area about some axis. So we'll do that next.